So now that we've identified using vectors in 2 dimensions, let's take this idea back into ideas of motion in 2 dimensions. So for right now, it's just generic 2D motion. Okay, so we kind of did an activity in class about this, and the idea is if we know how to add vectors and we know how to write vectors, so now we're going to apply them to some physical measurements. And so, something like if I have a point of origin, so this is my initial position, and then somewhere else I have a final position. Okay, now the path to get there can vary. We could go up maybe by 8 units, then we can go over to the right, say by 6 units, realize that we went too far the first time around and work our way back, and say that went back 1 unit. Okay, now if we wanted to know the overall distance that we traveled, okay, that would be easy, right? We would just add 8 units plus 6 units plus 1 unit. Okay, and notice that even though some are x's and some are y's, and the 1 unit is negative, and that we could still add them together, because in the end, distance doesn't care about direction. Okay, but if we wanted to find the displacement, first of all, graphically, the displacement would be the point that connects where we start to where we end. Remember, displacement only cares about final minus the initial. And so graphically, that would relate to a line that connects these points. Okay, and that line in space is a vector. Okay, and you'll notice that that line, even though we went up and over, we could really treat this like a triangle that starts off at the bottom and moves over what would account for 6 units, because you can see how that lines up with the yellow line, and it only goes up 7 units, because it doesn't go all the way up 8 because we lost a unit. Okay, and so with that in mind, now how do we find the displacement? So if displacement's a vector, okay, we can write it as it's 6 units in the x direction and 7 units in the y direction. But that's really as far as we can take it. If we don't have if they're x and y components, that's as far as we can go. Now, if we want to know the magnitude of our displacement, okay, how would we find the length of that vector? And we went through this in the notes. That would be a Pythagorean theorem calculation of 6 squared plus 7 squared. Okay, and when you do that, you will get about 9.2 units. Okay, now if we were to ask you what the average velocity is, so as a vector, the average velocity, okay, remember it depends on the displacement. Okay, and so it follows that there would also be a component nature to this. So the average velocity would also be the average velocity in the x direction and an average velocity in the y direction. Okay, and then you can calculate each one individually. What's important, though, is when we look at what the average velocity is equal to, okay, it's equal to a scaled factor of the displacement, because you'll notice it's displacement over time, but we can really think of it as a scalar multiple of the displacement, which means the scalar is going to change the magnitude, but it will not change the direction. Okay, so for that reason, if we go to our picture, the average velocity then would be a line that's in the same direction but it would be a little shorter in magnitude because you divided out that t value, which would shorten the length of our vector. So the velocity actually points in the direction of our two vectors. Okay, let's look at a different example on how that's relevant. Okay, so typically in your book, the position vector is typically written with an R. Okay, and the reason why they use an R, so this would be some x value, in the I direction, and some y value in the j direction. Okay, and the reason why we use R is because if you look at a coordinate system of just standard x, y, and if you wanted to go 3 dimensions with z, it would be the same thing. If I have a point somewhere out here, whatever value that point is, the vector that reaches out and touches that point is really like a radial line. If you imagine like a much larger circle, it's a line that points out from the center outward, and that's why it's given the label of R, because it's like a radial line. It points outward. Okay. So, good. So our R vector is kind of the generic way of saying a position vector in space. All right. So if I've got a position vector, say my first position vector points over here, so this is R initial. Okay, and then I have another R vector that points this way. Okay. The question is, if these were the two directions of my position, what is my average velocity? Or at least which way does the average velocity point? Well, again, average velocity depends on the displacement. Okay, and all the time does, since it's a scalar, is scales that down. Okay, so if we're going to find the average velocity, at least its direction, we have to know the direction of the displacement. So how do I find displacement? We know that it would be the final minus the initial. And we saw the other day in the last video about how do we add and subtract vectors. This is really like R1 plus the negative of R0. So if I do that with these vectors, I start with R1, and then I draw the negative of R0. So maybe something like this. Okay, and I pick that vector up, and that's what I draw here. I draw the two vectors from the same origin. Okay. So then remember, in order to add these vectors, we simply do a parallelogram type shape, and we find that the displacement would be in this direction. So if that's how the displacement points, it follows that the average velocity would point in the same direction, and the length is just dependent on how much time it takes to change the position like that. Okay, so that's kind of the idea, and you can almost see that here. If I were to pick this line up and move it to the tip of R0, what you'd see is you'd get this line, it's almost straight down. Okay, and you'll notice that if I redraw, rather if I could see, if I pick up R1 and move it, again, it would have to be perfectly to scale. All right, what just happened? Well, if I picked up R1 and I moved it, it would almost be like the average velocity vector points directly to the new tip of R1. Okay, so that's how we'd see this visually, is understanding how these vectors take place. Now the same thing applies with acceleration. Okay, if I take a ball and I throw a ball in the air, like say a football or baseball, and not just straight up, but I take the ball and I throw it up at an angle. Okay, I know this ball is going to follow a path where at every instant this velocity starts to turn. Okay, it gets more and more and more towards the ground. Now the question is why does it do that? Okay, if this is the velocity initial vector, and this is the next vector, and the next vector, and so on, why do these velocities keep changing in that direction? Okay, now once it's in the air, it enters free fall. And you'll be able to see that, well, if I do this idea again of what is the change in velocity, it would be the final minus the initial. And I apply that everywhere. So the negative of v0 would look something like that. And if I connect those dots, that would be the change in v. If I do the same thing between v1 and v2, I should see a similar change in v and a similar change in v across all the points. And that should make sense because remember, acceleration is the change in velocity. So the same idea. The acceleration vector is in the same direction as the change in velocity vector, but its magnitude is decreased because of the scalar of time. So that idea ends up causing this object's direction to constantly change. While at the same time, you'll notice that horizontally, right, at every point, this change in velocity vector points downward. So unless there's a part of our velocity vector, say v3, that's parallel to the change in velocity, the magnitude will not change, only the direction.